Hey guys, so we went over slides 1 through 6 in class. This is slide 1, as you can see. Using a table, analyzing a table to determine if it's linear or exponential. Well, look, you have 0, 1, 2. These are in a row, these are consecutive. But then it goes 4, 6, 8. It skips 3, skips 5. So be careful on this side if it's not consecutive, because then that means the outputs are not consecutive either. So anyhow, these 3 inputs are consecutive. We noticed that 7 times 2 is 14, and then 14 times 2 is 28. So that's our pattern. 28 times 2 would be 56. It would go with the input 3. 56 times 2 would be 112, and that does go with input 4, and so on. So anyhow, times 2, multiplying means it's exponential. Times 2 is my rate of change, and then my equation for an exponential is y equals a times b to the x power, where a needs to be the initial value, which is here at x is 0. Right, where the input is 0, the output is the initial value, so 7 is the initial value, and again 2 is the rate of change. So in y equals a times b to the x power in this format, again a is the initial value, which you in a table you can find it where the input is 0, find the output, that's your initial value, and then your constant multiplier is your rate of change, and that's b. So y equals a times b to the x. For this problem is y equals 7 times 2 to the x power. Like I said, we did slides 1 through 6. In this one, bank account starts with $42. Every month the amount is tripled. So it's tripled means multiplying by 3, which again, multiplying is exponential. Times 3 is our rate of change, starting with 42, so 42 is our initial value. And remember, a times b to the x, where a is the initial value and b is the multiplicative rate of change. So y equals 42 times 3 to the x power for this one. Here we have, careful again, these are not all consecutive. The only consecutive integers here for the inputs are 0, 1. So from 0 to 1, the outputs are 4 to 7. So my option is either it's adding 3, because 4 plus 3 is 7, or it's multiplying, and I'd have to figure out what I multiply 4 times to get 7. But as it turns out, it is adding 3, because 4 plus 3 is 7, 7 plus 3 is 10, and there's no 2 here to go with the 10, but then 10 plus 3 is 13, which... So, anyhow, it is definitely adding 3 to get consecutive outputs, and remember these last 4 are not consecutive, so we'd have to kind of, figure that out, what's missing, to kind of see that it is definitely adding 3 to get consecutive outputs. And then your initial value, where x is 0, y is 4, so 4 is your initial value, and it's linear because it's adding 3, right, as it says here. Since it's adding 3, it's linear, and remember, with a linear model, you're going to have y equals mx plus b as your model, your format for your equation, where m is the rate of change and b is the initial value. So your rate of change is plus 3, as you can see here. Your initial value is 4, and so that's b, and then you have y equals 3x plus 4 to model the relationship shown by this table. Slide number 4, it's definitely exponential. It's in the form of an exponential equation. Y equals a times b to the x power. The plus 54 is like a plus k, which you've seen in a couple different note sets or assignments. So again, it is in the form y equals a times b to the x power plus k, and so that makes it exponential. Another thing that you could say makes it exponential is because anytime you have an exponent here that's a variable, anytime your exponent's a variable, it's definitely an exponential function. So you can see the answer is exponential because it's in the form of an exponential equation. Slide number 5. Library has 9,784 books, and it's adding 621 more books each year. Adding a constant amount makes it linear. that's my rate of change, 621. Initial value, 9,784. So y equals mx plus b, where m is the rate of change and b is the initial value. M is always the rate of change, b is always the initial value. If it's linear, y equals mx plus b. If it's exponential, remember it's different. A is the initial value and b is the rate of change in the y equals a times b to the x equation. This one, identifying some key features. The type of function, guys, it's a line. It's definitely not exponential. It's linear. The x-intercept is where it crosses the x-axis, and you can see there it's 4, which is the answer here. The y-intercept, number 3, is where it crosses the y-axis, so right here, that's -3. Lines always have a domain of all real numbers and a range of all real numbers, as you see I wrote in here. It's because they will go forever to the left and right. Remember, left and right, that's your domain, that's your x-axis, and if it goes forever left and right, it goes from -infinity to infinity, which is aka all real numbers. Same thing with the up and down movement. The up and down movement, it'll go forever, and that's your y-axis, your range. So this line will keep traveling upward as it goes right. It'll keep traveling downward as it goes left, and so the range is also all real numbers. Lines don't have an asymptote, so NA for the asymptote. And state whether the graph is increasing or decreasing. It's increasing because, look at it, it's traveling upward. You always look at a graph from the left side to the right side. From left to right, it's going up, aka increasing. Number 7 is same. Identify the key features. Clearly, this is not a line. This is a curve. It's an exponential curve. So I'm going to go ahead and fill this one in. It's exponential. And number 2, the x-intercept, you could see is at 1. You could see right here it's at 1. The y-intercept is down here at -4. That's my answer for 3. The domain's all real numbers. It will definitely keep traveling to the left forever, and even though it's going up, it's also going right. It'll keep going up and right forever. It's all real numbers. It always is for the domain of the functions we're looking at. However, the range is not. It stops going down here. It never gets lower than -6, you guys. So y is always going to be greater than -6, and that's all you have to write on this. You got to kind of find where y never gets lower than, and identify, or where it never gets higher than. You'll have to identify the range as y is always less than something or y is always greater than something, depending on where the graph flattens out. So this graph, you can see, is always above. It's always above -6, so y is always going to be greater than -6. Remember the theory here, the idea, the concept is that this graph continues to flatten out here at -6, and it approaches the line y equals -6, but never actually reaches it. And then that line ends up being our asymptote. So I'm going to go ahead and draw that in before I identify it. So this function has an asymptote right here. It's almost like an imaginary line that the graph never touches. Whoops. The line's a little crooked, but either way, so this is my asymptote, aka the line that the graph approaches but never actually touches. So you have to state that as the line y equals -6. So the line y equals -6 is a horizontal line, and of course for this function it happens to be the line that it approaches but never touches, aka the horizontal asymptote. Increasing or decreasing? Well, remember, you always look from left to right, and from left to right this graph is traveling upward, up, 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 so that is increasing. Let's see, so number 8, we're supposed to be matching these here. Let's see what we got going on. Oh, whoops, that was an accident. Didn't mean to match those up. So I'm looking at all my equations, and I kind of have to decide what I have going on with my graphs. I can match those up with equations. We haven't done a ton of this, but you can do this. Here's what you want to do. you want to find the most plain equation that you can find here. The plainest one, the one that doesn't have negatives or doesn't have any adding or subtracting, right? Find that one. The one, because notice how they all have 2 and 3 to the x power. So find the one that's just 2 times 3 to the x power, this one. And then from there, well, I want to find the graph that looks like the most basic exponential, and I'm not sure how clear this has been, but this has to be the moment that it gets clarified, because we're about done with this unit. Look for the graph that flattens out at 0 and rises on the right side. It looks like this one, right? Rising on the right, an increasing graph would be the most basic exponential one with an asymptote at 0. And you can see the only ones that are increasing on the right are this one's, or sorry, rising on the right. Yeah, rising or increasing. This one's rising or increasing. This one's also rising or increasing, and so is this one. The other two are definitely not. This one's decreasing, and so is this one. So the one that flattens out at 0 is the most basic one. Okay, that is this one. These two go together. Now I have to kind of think back to what we went over. Well, what does this graph do? What can I do to this equation to make this graph, for example, to make this graph flip down? To make it flip down and look like this, right? So if I want to make the graph flip over the x-axis and look like this one here, what do I have to do? Okay, and so I do remember that if I change the 2 to a negative, I can make the graph flip down over the x-axis like this one. So which one has a -2? There it is. That will definitely make the graph flip down over the x-axis. So those go together. Now back to my kind of, let's call this our parent graph. Okay, so this is our parent. Whoops. This is our parent. I'm going to put the parent graph up in this corner here. And then from there, I'm just kind of identifying what makes the graph do certain things. So making the 2 a negative will make the graph flip down over the x-axis like this, right? You see the equation, the 2's negative, and the graph flip down. And I do remember what makes it flip to the left or right, however you think about it, but it's basically a flip over the y-axis. If I flip this over the y-axis, it'll look like this one down here, okay? So again, take this graph and flip it over the y-axis, it'll look like this. What do you do to the equation to make it do that, right? And so this equation, if you make the exponent, right, if you make the x a negative, the graph will flip over the y-axis. So that that is here. Make the x a negative, the graph flips over the y-axis. Those go together. And then the other two are just shifting this graph up or down. This is a little more obvious. The other two are definitely reasonable and logical, but you might have to do a little more thinking to see how it makes sense. But these are even more obvious. So what makes this graph slide up? What makes it slide down? Well, if I add a positive to it, it slides up. And if I add a net or subtract a net, or should I say if I subtract, I'll say subtract. If I subtract from it, it slides down. So the one that subtracts slides it down. So that's here. See how the graph has slid down on this one? So the one that has a -4 is going to do that. And the one that has a +4 is the one that's sliding the graph up. So that's this one. So those two go together. So, oops. That's really it for that. Definitely have a look at it, study it, see if it makes sense, ask some questions. Let's go ahead and go to the next slide. On this, so this is, you've seen this before too, where you have multiple representations for a function, a scenario, a table, an equation, graph. And so you have 4 representations, and you only have one of those 4 given to you, and you got to use that one thing that they gave you to fill in the other 3. So as you can see here, they give you the scenario, and then you're supposed to fill in the equation, the graph, the table. So let's see. The order in which you do it doesn't really matter. Population of bacteria is decaying at a rate of 60% every hour. The population initially started at 500. You count and record the population each hour. This is a little tricky because I don't know if it's telling me that there's 60% remaining or that 60% goes away and there's 40% left. So let's just say that since the wording's a little tricky, we'll just say there's 60% left, and if you happen to interpret it as 40% left, then that could possibly be acceptable, because we don't have a super clear written explanation, I don't think, necessarily. Technically, I would say it's probably decaying to where there's 40% left if it's decaying at a rate of 60%, but maybe not. Maybe there's 60% remaining. So either way, this is what we're going to say. Population initially started at 500. I'm going to go ahead and start with the table. If it started at 500 and then only 60% is left after each hour, well, 60% of 500, you guys, that's 0.6 times 500 is 300. And then 60% of 300 is 180. And then 60% of 180, let's see, use your calculator. 0.6 times 180. 0.6 times 180 is 108. Again, decaying at a rate of 60%, I'm just multiplying by 0.6. 0.6 times 108 is 64.8. So I suppose we could round that to 65, since we probably wouldn't have 0.8 of a bacterium. Okay, so again, decaying at a rate of 60%, starting out at 500, 500 times 0.6, 300 times 0.6, 180 times 0.6, 108, and so on. The equation for this, guys, it's definitely exponential, okay? Anytime something's changing by a percent, it's definitely multiplying. If it's multiplying, it's definitely exponential. So y equals a times b to the x, where a is the initial value, 500, and b is the rate of change, which is 0.6, and that's going to be to the x power. And then here, graphing this, let's just use these ordered pairs to graph. 0, 500, 1 and 300, 2 and 180, 2 and 180. Just got to kind of estimate that to the best of your ability. 3 and 108, 3 and 108 again, kind of got to estimate a bit. 4 and 65, same thing, kind of have to estimate a bit here. And there it is. And then we can see that it definitely looks like an exponential curve. So let's see if this can be drawn in. Whoops, sorry about that. Let me erase that. Try it again. So I'm trying to draw a smooth curve, and it's not that easy here with my trackpad. I'm sure give it one more try here. And then this graph would eventually, start to flatten out. So let's see if I can show that. Right, it would eventually start to flatten out, and it would start to approach 0, right? But never, it would actually get lower, right? But never actually reach it. So there's that. And go to slide number 10. Let's see, so slide number 10 only gives me a table. I'm supposed to write the equation. I can see the initial value here is 3. The rate of change, let's see, 0, 1, 2, 3, 4. So these are consecutive, which means outputs are also consecutive. It goes 3, 30, 300, 3,000, 30,000. This one's not too bad to figure out. 3 times 10 is 30, times 10 is 300, times 10. It's multiplying by 10. So it's definitely exponential. Right, if it's multiplying by 10, it's definitely exponential, which makes it y equals a times b to the x, where a is the initial value, 3. B is the rate of change, that is the multiplicative rate of change, since it's multiplying by 10, there's that, and to the x power. So y equals 3 times 10 to the x power. Let's go ahead and graph. Oh, this is not that friendly to graph. So 0, 5, 0, 3 is almost basically, we're just going to show that at 0 pretty much. 1 and 30, same thing. I mean, we could creep it up a teeny bit, but having 5,000 here means it would not really be showing. We wouldn't really be able to tell the way this graph is laid out. 2 and 300, I guess we could again creep up just a teeny bit. Again, we shouldn't be very close to 5,000 yet. 3 and 3,000 we can finally creep up to a little past halfway up, because 3,000 is a little more than half of 5,000. And then 4 and 30,000, finally 4 and 30,000 I can creep at 4, creep way up to 30,000, and finally it definitely looks like an exponential from that. And again, I'm going to try to draw this curve in. This one is obviously at 0 here, and then this is where it's flat, and that didn't work out for me. Let's try that again. Okay, let's see here. Okay, so it's hard to draw with the trackpad, but definitely an exponential curve here. And a scenario. Remember, you can make up anything you want, guys, for a scenario, as long as it makes sense. Like, you start out with $3 in a bank account, and it multiplies by 10 every year. Or you start out with 3 bacteria, and they multiply by 10 every hour. You can make up whatever you want, as long as the initial value and rate of change kind of correspond with what's happening. So, you start out with $3 in your bank, and it multiplies by 10 every year. Right? It's not a super realistic scenario. This almost looks more like a bacteria type scenario, but either way, as long as what you start with, your initial value, and your rate of change corresponds with this, at least it is showing that kind of what's the word? Everything kind of fits together, right? It all matches or corresponds. Each thing corresponds with the next thing. So that's it, guys. Definitely use it, do the quiz, and thanks for having a look.